Right, good afternoon, everyone. My name is Michael Dickens. I'm a research scientist with HPRC at Texas A&M University, and we're going to cover using the Slurm scheduler on the ACES cluster. This is an overview of what we'll cover today, and we'll have a break somewhere in between. So I'm going to start out with a basic architecture of an HPC and how ACES is set up, and then we'll learn about Slurm and configuring a job script with SBatch parameters. Depending on the type of job, if you have a single core or a multi-core job that runs on a single node, you'll have a specific way to set your SBatch parameters. For multi-node jobs, just a little different, but there are different ways to run multi-node jobs. We'll cover MPI jobs in TAMU Launcher. Actually, we're not going to cover array jobs, but we do have documentation on that. And then we're going to show you how to monitor your job once it's running, once the job's complete, looking at logs and debugging if there are any errors, and also to see resource usage for completed jobs. So this is an image of the ACES cluster, and you can see in the list at the bottom we have quite a number of accelerators available. Some of these are in a composable state, and I'll talk about composability in a little bit, but some of these are not yet in a composable state. So we're going to be using the portal to access the command line. So what you first want to do is go to our main web page at hprc.tamu.edu, and on the menu here, click portal, and then you'll see access portal, ACES portal access. So I'm going to show you where this is. Here's the menus, drop down menu, and we're going to use the ACES portal. And then you'll probably reach this screen first. If you haven't logged in already, you'll select however you set up your access ID. I just happen to use my Exceed ID, so I'm going to select this. And then username and password. And then it's going to, actually in my case, I've got it set up to give me a phone call. All right. So once you've completed that authentication, will bring you to the ACES portal. So you do need an access ID in order to access the ACES cluster through the portal. Right. So we went over that. So if you can show us, raise your hand and show us if you've logged into the portal. There should be a way to raise your hand. All right. Okay, good. All right, so the part of the portal we'll be using today is the command line. So once you're logged in, the clusters menu on top, select ACES shell access. ACES shell access. Right here. All right. So once you've logged into the portal, connect to the command line, which we just did, and what information do you see, and on which login node did you land? So if you want to just post in chat which login node you landed on, I landed on ACES login 3. So I can increase the font size here. We have others logging in, login 1, login 2. Let's see. All right, good. You can see, so we have links to our user guides, and we have information about the status of the cluster, whether or not there is a maintenance coming up soon, and also some messages about not to use too many cores on the login nodes. And we'll talk about what is a login node and what is a compute node in a little bit here. All right. So nodes, cores, and queues. So we've had some questions about what is a node, because often we'll just throw out the term node. There's two types of nodes for that users will be using, login node and compute node. So we all access the cluster through the login node. That's when we saw, what do we see? It says login 3. All right, so we know we're on a login node. Compute nodes, these are the nodes that actually do the computational work. When you schedule a job, the job is sent to the compute nodes. Login nodes, this is where you create your job scripts, do some file manipulations, and run some test Unix commands. You can also test some software, install software. Just be aware that processes are limited to 60 minutes. They'll automatically be stopped once a process has reached 60 minutes. So be aware of that. Compute nodes are the nodes that have the accelerators, GPUs, and other accelerators. So you'll hear the term core, CPU, and threads used often, and you can consider these to be very similar. Slurm uses the term CPUs. You might be familiar with the term core, and a lot of software uses the term threads. So we're going to use those. One core is the same as one CPU, is the same as one thread. A queue, this is the list of scheduled jobs, and we'll see how to check the queue for your running jobs. All right, here's a diagram of a typical HPC. So we have the login nodes. In that case, we have 3 login nodes, and then we have a lot of compute nodes. So the login nodes are for file manipulation, prepare your job script. I mentioned that earlier, testing, installation of software. And then you want to keep processing the less than 60 minutes and using no more than 8 cores, because we have a number of people logged into the same login node. So if you overwhelm the login node, it's going to cause other people's processes to slow down. And also be aware of the amount of memory you're using for whatever testing you're doing. You don't want to use too much of the memory, because that will really slow the login node down. Compute nodes, these are where the jobs are scheduled. I'll show you how to configure your job scripts to use the maximum available resources on the compute nodes. And these are for jobs running more than 60 minutes, several days. So we'll go over that. So what is a composable cluster? So on the left, in this first green box on the left, this is a traditional configuration where you have this blue box represents a server, and you have accelerators and SSD drives plugged into the motherboard on that compute node. So you can see we have examples of 5 different compute nodes, and each of these components are plugged into the compute node. So this GPU is only available to this server, and the bottom, these 4 GPUs are only available to the server on which it's plugged in. Composability is is a new way of configuring compute nodes. So we have a pool of composable resources, and here we have, in this case, we have server pools represented by these blue boxes, different accelerators represented by these green boxes, and storage and memory pools represented by these red boxes. So ideally at runtime, whenever you want to schedule a job to use, let's just say 1 FPGA and 2 SSDs, you'll schedule your Slurm job script in that way, and then this Liquid Fabric will configure a compute node to have those resources that you requested. So you can see a compute node can be changed. The configuration of a compute node can change. It can have 1 FPGA, 2 SSDs, 4 GPUs, SSD, or multiple GPUs. And we'll go over how this is done later in the presentation. So if anyone has any questions during this short course, please raise your hand or just unmute yourself and ask a question. If you have a question when we're on a slide, that way we can cover it. All right. Batch computing, we use the term batch in a sense because we put a batch of Unix commands in a job script. So access users will log into the login nodes, but we need to use the resources on the compute nodes. So how are we going to do that? This is with a batch script. We create a batch script, which is just a text file, and it contains the SBatch parameters, and you also put your software commands in there. The SBatch parameters are read by Slurm to request resources on the compute node. If they are available, if they're not available, your job will be remain queued in a pending state until resources are available. And once they're available, your job will be scheduled on the available compute nodes. All right, at times the cluster can be busy. You can check how busy the cluster is. You can use the sinfo command. It gives you a lot of text output. If you look at this carefully, you can tell the different partitions, and each partition has a time limit. For example, the CPU partition has a 7-day time limit. GPU partition has a 2-day time limit. There is some information here about how many compute nodes are actively running jobs, how many of them are idle, and how many are offline, and the total. So you can see in this case, when I ran the sinfo command, there were in the CPU queue, there were 0 nodes that actually had a job running on it, and there were 65 idle nodes. You can also go to our webpage and look in the left panel, and it will show you how busy the cluster is at that time when you launch the webpage. And you can see, you can actually click on this, and it will take you into give you some more details. Let's see if I can go back to there. Just pull this page in. All right, on our main web page on the left here, you can click on this and you can see which jobs are running. These are all the different jobs for all the users, and you can see what types of jobs are currently running. You can also come and see the historical status to see how busy the clusters have been over time, and you can set the number of days, and you can either select percentage of cores, percentage of nodes, total nodes. You can change, just click update once you change the statistic. All right, so one thing you may want to know is how busy are the GPUs, and are there any available for my job to launch right away? We have a command called GPU avail, and you can see this is the output. It would change over time, but this is just an example. right now at this point when I ran this, there were 15 nodes that had 2 H100s attached and 1 node that had 6 A30s attached. And then this availability will show you which nodes are available for jobs. Now the A30 node at the bottom has all 6 GPUs available. There's 6 GPU count, there's 6 available. It also shows you the available CPUs and memory. The second node, AC046, there's only 1 GPU available. So if you want to use that GPU, you'll have to schedule 48 CPUs or less and 244 gigabytes of memory or less. And if this was the only H100 available and you scheduled 1 GPU and you scheduled all the memory and all the CPUs, you wouldn't be able to run a job on this node because there aren't that many CPUs available and memory. So this is helpful to know that if there's only 1 H100 left, it'll let you know how much memory and how many CPUs to configure your job script. All right, this is an example of a job script, but again, it's just a text file. This very first line, you will have this and not change this, leave it exactly as it is, and don't have any spaces after the word bash. Then after that, we have sbatch parameters. Sbatch parameters begin with a pound sign and sbatch all caps, then a space and 2 dashes. And then you've got whatever the parameter is. For example, job name. So you need to type this just exactly as it is. Don't replace this dash with an underscore or leave it out. Dash job dash name equals. Call the name whatever you want. Keep it short and concise because whenever you view your jobs with the SQ command, it will only show you the first 15 characters or so. And also avoid using spaces. If you do use spaces, you can put quotes around it, but generally, it's a good idea to not have spaces in the job name and also in your directory names and file names when you're on a Linux system. Here's the time. Format is days dash hours colon minutes colon seconds. So it'll be easy if you want to change it. A job script from 1 to 5 days, all you need to do is change this number here instead of trying to calculate how many hours in 5 days. Nodes, this is basically what it says. How many nodes do you want to use? In this case, this is 1 node. In tasks per node. So the way I remember about what a task is, if you think of it as a command. So if I'm running one command down here at the bottom, if I'm running 1 spades command, how many spades commands do I want to run per node? In this case, I'm going to run 1 spades task per node. And this task is only going to have 1 CPU. So I've matched the number of CPUs that I have in my sbatch parameter with the threads option for my spades command. And also I'm requesting the lowest amount of memory that still charges me that still corresponds with just 1 CPU, which is 5 gigabytes. And then we have a couple of output files. This is useful for debugging, and the %x will append the job name to the output file, and the %j will append the job ID. So you'll have a standard out dot, and in this case, it'll be spades dot, and then a job ID, which is generated at runtime. And this helps you during debugging purposes. And you can leave out the standard error line, and it will put standard error and standard out in the same file. But it might be easier to debug if you separate these two like this. The first thing you want to do is unload any modules. We've had some users that put some load modules in their bash RC environment, and they're automatically loaded when the job runs, and they can't figure out what's going on. So as a general rule, we just do module purge. Then load your modules. We do have a module hierarchy, so you will be loading dependencies first, the toolchain dependencies, and then you'll load the software version. This is all case sensitive, so it has to be exactly as it's presented when you're searching for modules. And then you run your commands, however many commands you have. In this case, we have just one command, and then we match the threads with whatever we selected up at the top. Now your job script, you can name it whatever you want. Some users call it .jobs, some it .sbatch, .sh, .slurm. I would just recommend you be consistent, because in the future you may want to search for all your job scripts. And if you know what you name them, then it'll be easy to find using the find command. All right, the next few slides are going to have a lot of information on it, but it's more of a reference. If you have any questions over any of these, you're welcome to ask. Basically, nodes, you just change this from 1 to the number of nodes you want to run, you want your job to use. It defaults to 1 if you're using 1 CPU. Obviously, if you're using only 1 CPU, or if you're using 1 task, if you're only running 1 task, it can only run on 1 node, so it will default to node. Nodes equal 1. You don't have to worry about this. We're not going to cover arrays, but you don't need to use nodes with arrays. In tasks, this is a different way to request CPUs. So you can think of a task as a command, like we talked about the spades command. You can set this in task equal 1. This means that there's going to be just 1 task, and by default, it will run on 1 node. We'll also cover this later. When you run in task greater than 1, and if you don't use the if you don't specify the number of nodes or the number of tasks per node, your job may be scheduled on multiple compute nodes, and then you'll be wondering why your job failed because it ran out of memory, although the Slurm SEFF command shows that you had plenty of memory. So you want to use either nodes or task per node. And I'll go over that more in detail later on a later slide. CPUs per task, in this case, you can use a maximum of 96 tasks. Just an example, a task can be considered like a command, and then your CPUs you can use with the software. If it has an option for threads, you just use that CPU value for threads. All right, here's some more that you will most likely have in almost all your job scripts. You'll need a time. You'll need to specify the time. If you're not sure how long your job's going to run, if you have enough service units, or if you have enough, or in the future when we configure service units, you'll have to think about that. But for right now, you can just configure your job to run the maximum amount for whatever partition you're using. In this case, this is an example of running it on 7 days. And then later, if you're running multiple job scripts similar to the one you just ran, and it only took a day, then you can drop this down to like 3 days. That'll give you time in case your data set's a little bit bigger and it takes a little bit longer. So you may not need to schedule every one of your job that you run for 7 days. Once you get an idea of how long it takes, based on how many resources you select. Memory, you do need to include this memory parameter. The maximum on ACES is 488, so you'll have to have this. You can specify as G, 488 gigs. Job name, give it a job name. This will help, especially if you're running multiple jobs, you can tell which ones are still running, which ones have completed, because they may be in different directories. Output and error, covered that earlier. Partition, by default, the CPU partition, you don't need to put this in there, but if you're using any special partition like GPU or some of the other partitions like members, you do need to have this parameter in there. All right, if you're going to use GPUs, you'll have to let Slurm know this by using the --gress parameter, and you can specify how many GPUs and the type of GPU. GPU avail, you can use that command to see what's available at the time in case you want to get your job running right away. If the H100s are busy and you want to see if there's any A30s available, then you can run GPU avail, and if there's an A30 available, then you can change your job script so that it would start on the A30 instead of waiting for the H100s if you want to do that. You can change the number of requested GPUs by changing this, the last part here. In this example, there's a 1, you're requesting one H100, you just change it to a 2. To use 2 H100s, you'll want to make sure that there is a configuration that has 2 H100s, because we may change it and we may have a maximum of 1 H100 on several nodes, or we may have a maximum of 4 H100s on fewer nodes. You will need to include also the partition equals GPU to let Slurm know which partition you will be using. Account, this will be something in the future, but you can, if you want to use a different account number than your default, you can add this in your job script. You can also add parameters so that you get an email whenever the job begins, it ends, fails, or you just want to email at every step. Just be aware that sometimes people will write a job script that submits multiple job scripts, and then at each point when all of those job scripts begin, and you'll get an email. So you might get a lot of emails. So be aware of how you configure this. You can schedule one job to start after a previously running job or previously scheduled job completes. You just have to add this dependency equals after OK, and then the job ID. And you can get the job ID. If you launch one job and you want to get the job ID of that job, you just run the sqe-me command. It will show you your jobs, and then you can get the job ID and put that in your second job script. All right, submitting jobs. We're going to go through submitting a job script in a little bit, but basically the way you do it is once you get your job script composed, then you use the sbatch command, sbatch, and then whatever the name of your job script is. You can submit it using this approach. You can also submit it using on the command line like this, although this first approach will give you all your sbatch parameters in the job script, while the second one you may not have a record of what parameters you used for long, since your history may be overwritten over time, your bash history. You can also start an interactive session using the srun command. This will start a job script. This will start a job on the terminal directly to a compute node terminal, and then you can run testing commands or running computational work that way. Just be aware that if you schedule one task for a interactive job, that you only use one CPU. If you configure one CPU per task, you only use one CPU in your commands. And also be aware, some software you have to specifically specify the number of threads to use, or it will find all the threads on the system and just use them all. So be aware of how you configure your interactive job, but also be aware of how the software is running, whether you have to specifically specify a number of threads. All right, so now we want to know, I want to configure a job script, and I want to know what is the maximum number of cores and the maximum amount of memory I can configure in my job script. So we have this tool called max config. This will show you the different partitions. This information you can also get with the sinfo command. If you remember on the previous slide, we saw the different partition names. So in this case, it will list the current partition names and also show you the GPU configuration on the cluster. In this case, we have A30s an A30, at least one A30 node that has 6 GPUs attached, and we have at least one. It doesn't tell you how many are here, but you can get that with the GPU avail command. There are H100 nodes, where we have 2 H100s connected to the compute node. This will show you the maximum. Default is the CPU partition. It will show you the maximum number of cores, memory, and time for that partition. So the maximum time for a CPU job is 7 days. The maximum CPUs per task for one task is 96, and the max amount of memory is 488 G. Now, the mass config shows you these SBATS parameters for reserving the entire compute node. Now, there's different ways to reconfigure this to still request all the cores and memory on a compute node. You can actually switch these values. The number of tasks per node is 96, and CPUs per task is 1. We'll cover that in a later slide. So this will print out information that you can copy and paste into your job script. All right, so let's take some time to get familiar with this utility. You can run the maxconfig-h command to answer these questions. So what options can you use to see the maximum resources for H100 GPU? So if you want to just post the command in chat, and we can see if everyone's getting a hang of how to use this utility. The maximum resources for an H100 GPU. So run maxconfig-h first to see the options. All right. One answer. Let's see. I think I have to come back here. Okay. Right. So maxconfig-h shows you different options you can use. You can just run it without any options, and it'll show you the default CPU partition. So to see for the H100 or H100 node, you just use GPU H100. And it will show you to use one node. Right now we have nodes that are configured with 4 H100s. And if you're going to use all 4 H100s, you're going to use the entire compute node for your job. So you'll also want to just request all the CPUs and memory, just so your job doesn't get halfway through and fails because you only requested 10 gigabytes of memory. So notice the GPU partition is fewer days than the CPU partition, and you can get this information by running this command, and it may change over time. We may change this to 4 days or back down to 1 day, but right now the default is 2 days. All right, next one. What is the maximum number of H1 GPUs available per node? All right, we pretty much answered that with this output here. Right here is the maximum H100s is 4. Here it is 2. So actually, you can run the GPU avail. This will be a little different than what we have on the slide since we changed the configuration. And you can see that there is one node that has 4 H100s attached. There's one node, but that node currently is not available, being used by other jobs. So if you want to run this on a different cluster, this is a tool that we installed locally. You're definitely welcome to use this tool. It uses the Slurm S-control show node command, and it gathers information from all your nodes, max amount of memory, the number of partitions, number of compute nodes in each partition. You're welcome to, this is open source code, so you're welcome to use that on your cluster. We may need to do a little bit of adjustments in order to make it work on on a generic cluster, but for the most part, I think the only thing that may be different is if your cluster uses charging service units, then you'll have to configure that in the GPU avail code. It's just a Perl script, and you can see where you can change. You can see where you can change the service unit charge per accelerator, or you can just with using one option in there, you can disable charging so it doesn't show you charging. Right now, we don't have we're not charging service units. We don't have that enabled right now. But when we do, this max config output would actually show you how many service units your job will require. Yes, what I'll do is I'll have to create a separate Git repository so that we can make this more generic, so it'll work on your cluster right away, just as soon as you install it, or as soon as you download it. All right, what's the maximum runtime for H100 GPU job? That's in the output too. 2 days, right? We answered that. All right, what max config option can you see the maximum resources for just one H100? So post your command in the chat, and we'll see what it takes to see the max resources for just one GPU. So we got the first part, selecting the type of GPU. Now we want to only select one GPU. If you select just the type, it's going to show you how many, the maximum. But if we want to change this number to a 1, how can we do that? Right, -G1. So now what we see, the max time is still 2. Still have 1 node configured in this case. But CPUs per task, it used to be 96, now it's only 24. And memory available was 488, now it's only 122. It is showing one H100 GPU, so you can copy and paste this to schedule a job on one H100 GPU. So why doesn't this option show all available memories and cores on the compute node? Anybody want to take a guess at why we configured it to show you only a fraction?
Are you guys like splitting the nodes up between different users if people are only requesting like one GPU at a time?
Well, there's still 4 GPUs plugged into this node right here. But the thing is, if you request just one GPU and you request all the cores and all the memory, then those other 3 GPUs are not available for other jobs because there's no available CPUs and no available memory. So in this case, what you'll want to do is select just a fraction of the cores and memory so that other users can use the other 3 GPUs. So currently the way we, I'll cover this later about composing nodes and why we need to scale the resources now, but in the future you won't need to, because you can configure a job that will configure the resources at runtime based on your Slurm parameters, so you won't have to scale the number of CPUs and memory down. You can use all the memory, all the CPUs, and then select the number of nodes you want to attach to that. But we're not at that point yet. But for now, if some software can only run on one GPU, so in this case, you can select one H100, but you don't want to select all the memory and core unless you need it, unless you know that you need it. That way, at least half of the memory and core can be used for a different job. And so this, you don't have any idle H100s unavailable because you only used one H100 and you requested all the CPUs and the memory. I have another slide to cover that later. Okay, what can we use to see the bitware partition? Here's the bitware. So basically you just give it the P for partition. And it will show you bitware. It will give you the partition parameter that you need and show you the number of cores, memory, and the time for that partition. All right. So as I mentioned earlier, there's different ways to request all the cores and memory on a compute node. In this case, I'm showing you examples for a single node job. Maxconfig uses this first example, where it will set in task per node to 1 and CPUs per task to 96, and all the memory this is total memory per node. So if you switch this to 10 nodes, you don't need to scale the memory. You just keep it at 488 G. You can also set the number of tasks per node to 96 and CPUs per task to 1. And some software, it doesn't matter how you set this. It just wants to, you just want it to use all 96 CPUs. When you're configuring MPI jobs, this can be important. If you have 96 tasks, each one has one CPU, or whether you have one task and 96 CPUs. Because once you scale this across multiple nodes, you want to make sure you're running the correct number of tasks per node that your MPI job is using. You can also do it this way. You can use in tasks. In tasks, to me, can be a little more confusing because you do need to specify nodes or CPUs per task, or task. I'm sorry, you need to specify either nodes or task per node, or your job can run across multiple nodes. And here's an example of you either use number of nodes or you use in task per node. So that in this case, this is for a single node job. So either specify nodes or specify that you're running all 96 tasks on one node. So this is what you don't want to do. You don't want to specify 96 tasks and not use all the memory. If you specify all 96 tasks, you're using all 96 cores on the compute node if you don't select the number of nodes. And what will happen in this case is this job could be scheduled across multiple nodes. So you definitely want to use in task per node or nodes together with in tasks. And also you want to make sure that when you do submit your job, if you're using in tasks, you want to check to make sure you got it configured correctly and that your job was only scheduled on one compute node if you wanted it to run on one compute node. All right, single node jobs. Single core jobs, there might be some software that can only run on a single core, and there might be steps within software that only run on single core and later steps run on multiple cores. So you need to decide whether you want to use a single core job or a multi-core job. Again, remember, some software will use all the cores that it queries on the system, So look for the threads or CPUs options in your software help documentation to see if you need to set that. The idea is that if your job supports multi-core processing, then select all the cores to get your job completed as quickly as possible. And if you're going to select all the cores, select all the memory, since you will have your job will be the only job running on that compute node. There's a way that you can, if you have a lot of single core commands, you can run this as a multi-core job. Basically, you're running a lot of single core commands using this utility called TMU Launcher, which we've developed. And we'll go over that later. I'll show you how to use that. All right, in tasks, this is just kind of repeating what I said earlier. Make sure you use either nodes or task per node, or your job may be scheduled on multiple nodes. All right, requesting one GPU. So currently, the way composability works on ACES is we have a request that we want, for example, we want 6 A30s on one compute node. So then we can use software utilities to do the configuration, and then once the configuration is complete, then we update the profile of the A30 GPU type to reflect that there are 6 GPUs attached. We don't actually have to go and pull out GPUs and plug them into different machines. It's all handled by the software. But for now, this is not done. This doesn't happen at runtime. In the future, it will be integrated within Slurm, so that however you set your Slurm job parameters, the compute node will be configured at runtime when your job is launched. This is just showing a GPU avail command, which we looked at earlier. Run this to select what type of node. Maybe if you're not specific to using H100 and there's only A30s available, you can get your job launch started quicker. Just remember that if someone's running, let's just say someone's running an A30 job with all 6 A30s, and the maximum runtime is 2 days, and they may take up 2 whole days running a job using the A30s. So if you want to get started right away, just see what's available, and then you can change your job script. So hopefully it'll start up right away. Here's kind of an example of what we covered earlier. Selecting A30 and 4 A30s, 4 out of 6. This just shows you it'll scale the memory and CPUs per task so that the other 2 GPUs are available. Again, in the future, when composability is done at runtime, we won't need to scale the memory and the CPUs per task. All right, max config, like we saw this earlier, just run it. It shows you the default for this CPU partition. We did this earlier, max config for the GPU partition. In this case, when I made this slide, there wasn't a GPU, there wasn't a compute node that had 4 H100s attached, but now there is. Right. All right, here is basically we're looking at the output of the SBatch parameters, the output of max config for the recommended SBatch parameters for a H100 job. In this case, if you're using 1, just showing you that cut back on the CPUs and memory for now. And then you can run your commands afterwards, loading your modules and running your commands. Again, this number can change, and we just saw that it did change from the maximum for H100s on a single compute node, change from 2 to now it's 4. We do have a maximum, we have a total of 300 H100s on ACES, and a total of 6 of the 830s. And just a reminder that if you request 48 CPUs per task, check your software command and make sure that you specify the matched number of tasks or CPUs with the threads option, or whatever option your software uses. It could be threads, it could be cores, it could be CPUs, but just search the documentation for that software to find out what option to use. In this case, it's threads. And in the example 2, if you're going to reserve all the, again, if you're going to reserve all the CPUs, reserve all the memory so your job doesn't fail halfway because it ran out of memory. All right, you can use a Slurm environment variable. It's Slurm CPUs per task, all uppercase. This will take the value from whatever you put in CPUs per task. So if I put 96 here, then this variable automatically updates to 96 when the job is submitted. Then later, if you want to reduce the number of CPUs, you only have to change this number, and all of your commands down here will match whatever number you changed. That way you only have to adjust it in one place. Because you might have multiple, you might load a module, run a command, and then module purge, load a different set of modules, run a different command, module purge, and each of those commands may have an option to specify the number of threads. And instead of hard coding all the number of threads throughout all your commands, you can use this variable. So it'll capture whatever you have up here. All right, multi-node jobs. Basically, just test it on a single node first to make sure everything's running correctly, and then you can scale it up by changing the number of nodes. There's information here. You can go through that, and it's just showing you based on whatever parameters you select, you'll get different numbers of, you might get different numbers of CPUs per task. Just make sure you're aware of how many nodes you're using, and to make sure that your software supports running across multiple nodes. So MPI job, MPI run will read the parameters that you have in your Slurm S batch lines up here. So you don't need to specify the number of tasks per node or CPUs per task in your MPI run command. MPI run reads this information up here. And again, if you're running one task per node and 96 tasks, 96 CPUs per task, or 96 tasks per node and 1 CPU per task, you'll need to update this accordingly based on whatever you're running here. So you can get the information from maxconfig, but you will need to switch these two values based on how your job is, how you want your job to run. All right, TMU launcher. If you have a lot of single core commands that you want to run, let's just say you have 1,000 commands. Instead of submitting 1,000 jobs, so what you want to do is you want to submit one job that has 1,000 commands in it. So you can run TMU launcher -H to see the help. Basically what you need a commands file. And in that commands file is where you have each command. So if you have 1,000 commands, you'll have a commands file that has 1,000 lines. Each line is a command, probably processing a different parameter or a different input file. And then you want to configure all the memories and cores on the compute node to get as many of your single core commands running per node. So commands file, here's an example. I'm using this software called Spades. Let's just say you have 500 commands. We can only show you a few here, but basically you have your Spades command, your input files. You can see sample 1 through sample 22. And you have different output files, and you're also going to specify the number of threads per command. So you'll need to generate a file. In this case, if you're going to use this software, you'll need to generate a file that has this command in here. And then you'll want to increment it accordingly based on the input file names and the output directory names or file names. So creating this commands file, there's ways you can do this on the command line, and we're gonna do that in the next few slides. And just showing you in this example, you can configure your job to run 96 tasks per node and 1 CPU per task. So it's going to select 96 of these, the first 96 commands in your jobs file and your commands text file. And it's going to put those on one node, and the next 96 commands are going to run on a second node. And then once one of those commands or one of those tasks completes, it will read your commands file and take the next command in line and start running that one. If you run out of time, if you specified 1 day and it takes 2 days, when the job finishes, it will say that it failed because it ran out of time. But you can look at the status of the job, the TMU launcher status, and it will show you the last command that completed successfully. You can just run your job script again, and TMU launcher knows to pick up where it left off. So loading, you only need to load the software in your job script, not in the commands file. These are two separate files. So your commands file only has the commands in it, and your job script file is where you load software modules. This is just showing you if you want to use 4 threads per command, then you would change the number of tasks per node to 24 and CPUs per task to 4, because you know the compute nodes have 96 cores total. So that way you can fit 26 tasks on one node, on each node. Each of these tasks where you're using 4 CPUs. Some software uses this OMP num threads environment variable. If you need to use this, you can change this number to match the Slurm CPUs per task. This by default is set to 1. OMP num threads equals 1. And sometimes when you run your software, you specified all the CPUs here, but your job only used 1 of the CPUs. Search the documentation to see if you need to set this flag or set this environment variable in your job script. All right, so what we're going to do is we're going to take some time here to see how we can create this commands file. And we're going to create some empty files with this first command. We're going to go to, we can do this in our Scratch. You go here. Okay, so I'm going to go to Scratch. Okay, I'm in my Scratch directory. All right, you can run this if you can copy and paste. All right. So I created a directory called seeks, and in each of those, each of that directory, I created an empty file to represent if I was to have sequence data. And this creates a sample name. It's just an example that we use for this tutorial. Okay, so once you've run this command, you can see I've got all my output or my input files. So what I want to do is I want to get the sample names. So we need to get the sample name. In this case, the sample name is either S1, S2, S3, all the way to S40. We just want to capture the sample name in a variable. Okay, so on the command line, there are ways to create variables and change what's in the variable, or select just part of the variable. So in this case, the very first command here, it will create a variable called file. So commands or variables on a Unix system, you assign them without the $, but in order to see what's in the variable, you use a $. So echo $sample. If you want to see what's in the file variable, you can do it like this. Right now, the file variable is empty. So copy this. Yeah, this presentation, it's on the web page on the we put the page in the link in chat, so you can go there and open up this presentation and see if you can copy. And the way I'm doing it is I'm just highlighting it. Highlighting, it's kind of hard to see a little bit there, but highlight, copy, go back to the terminal, and you can actually do Control-V to paste. All right, so that command assigns a value to a variable called file. Now, if we echo file, I'm just using up arrow to go to my history of commands. So if I now have echo file, the contents of my file variable has what I assigned to it. Seeks sample1 r1 fastq.gz. All right. So this basically just creates a variable named file. You can name the variable whatever you want. Just make sure you don't overwrite any variables that are already defined. Generally, the system variables are all uppercase. So if you wanted to see what's in the variable user, there's already something populated in user, so you don't want to reassign that if you need to use that variable or your software needs to use it. You can also, if you want to see what environment variables there are in your session, you can do the env command. It will show you a lot of variables. And here they are. So there's a lot of different variables: host name, pwd. Here's the home directory. There's you can view those. So Control L, clear my screen. So I'm looking at seeks, and I've got the first command in assigning a value to a variable. Now, if there's a Unix command called base name, so base name and then your variable with a $sign in front. And for Unix commands, you can hit tab and it will complete the command for you, and then file, base name of file. Now notice what base name did. It stripped off the directory path. So now all I have is file name. All right. So is everyone at this point caught up? Do I need to review anything? This can get a little complicated, but if you just type in these commands, you'll get an idea of how these commands work. And you don't have to remember them. You can come back to this slide as reference. But after you use these, you'll remember these. There's just a few commands here, but after a while of using these, you'll realize how helpful these are. All right, so we still need to get this S1 into a variable. So the next step is we want to capture the file name into a variable called sample. So this previous command, we can capture the output of that command by using $ and parentheses around that command. So capture the output of one command into a variable by using this $. parentheses. All right. So it didn't print out anything because all we did was assign a value to sample. Now we actually can, now we have this in a variable which we can manipulate. So now we have the sample variable populated, and note that whenever you're setting these variables, if you log in next time, these variables are only for this session. So if you log in a different session, if you log out and log back in, these variables are not in your new session. So now what we want to do, what this part does is it will strip off the underscore R1 festview.gz from whatever's in your variable. And the way you do that is $ braces / and whatever you want to remove. So copy and paste this and you can see how it works. Copy. So now we actually did two things. We echoed sample, the contents of the variable sample, but we want to remove this ending part. So now we were able to capture the sample name. And then the last part, if you want to replace part of the value that's in a variable with another part with a different string, you can use this. So this is a way you can get the second file that goes with the first file. In this case, these are sequence files, so R1 and R2 need to stay together, at least in this spades command. So we can actually just change part of the value that's in the variable to a different string. You just use / whatever's on the string / whatever you want to replace it with. So this is very useful. So there's just a few things. If you're not familiar with this, we've only done a few things that you may not be familiar with. Base name, how to capture a command inside of a variable, and how to remove or replace text that's in a variable. So this tells you what you're doing, stripping off R1 text or substituting R1 text with R2. All right, now what I want to do is I want to do a loop through all the sample names and actually write the command. So again, this might look a little complicated, but basically what we did in the previous slide, we're just putting it in a for loop. This is the syntax for doing a for loop in Bash. So again, you can just copy and paste this because you might make an error in the with a dot or a dash. But in the future, basically what you can do is run this, check your commands, make sure they're correct. If it's incorrect, you can use the up arrow, and then you can edit your previous command, run it, create a new command file, and keep doing that until you get your commands correct. So basically, I'm just going to copy this. These should look familiar from the previous slide. We're assigning one variable with the value from a different variable. In this case, it's the file. We're replacing R1 with R2, getting the base name of that file, and then we're echoing the command, this software command, and saving it to a commands file. So I'm going to paste that in there. Done. Okay. Now we want to make sure that the commands file is correct. So we're going to do cat command, and I hit tab to complete it for me, and we can see that it created this file with all these commands in it. And they're not in order. Actually, it doesn't go from S1 to S40, but you can see we got our command file now. One command is a spades command with the input files for sample 10, output directory for that command, and the number of threads. And again, if you want to change that, you just hit up arrow. Now let's just say you want to change threads to 4. Now you can just change that to 4. And then look at your commands again. We'll just look at the first few commands. All right, so you can see now that it did change the output to 4. So if you are using creating job scripts that run hundreds or thousands of commands, you can do this in Excel, which people have done. But once you get the hang of it, this is very useful on the command line, and there aren't that many steps, or not too many new commands you need to learn. You may not ever have to use this. You might be doing simple job scripts, but in case you do get to a point where you have 500 samples you're running, you may need to create a text file with 500 commands in it. So this won't be for everyone, but it's here for reference, and you can get an idea of what you can do on the command line. Now, this is something more complicated. In the previous example, it was easy to strip the last part off of 2 files because we know it is actually easy to strip off this part because it's the same for both files. But what if it's different? There's another way you can use. This is actually different ways to do this. Substring is whatever you're searching for, and variable is whatever the variable name is. But these are the parts that you need to use to actually do this part. So this is a reference. I don't know how to do this off the top of my head. I don't use it that often, but it is very valuable if you are creating thousands of commands to run in a TMU launcher job. You can refer to this slide and test it out. Test out to make sure you're using the correct pound and dollar sign, or pound and asterisk %. And basically it's a reference slide. And so if you want to run this, you can run this. And we're going to actually take a 10-minute break right now. And if you want to work on this, you can. And if you have any questions about this, you can ask them when we get back from the break or during the break. So we'll take a break for 10 minutes, and then you can either work on this or you can wait till we get back to continue. And we won't cover this. Basically, what I have here is the command and what you're going to see in the output. Assigning a variable, you don't see any output unless there's some error in spacing or the way you created this. If you echo the file, you're basically seeing what's in the variable you created. Then this is a way to substitute after the underscore, after the first underscore, all this information after the first underscore. Then remember the base name of the file. We can get the sample name, save it into a variable, and then we actually have the sample name. So you can work on that, and we'll be back in 10 minutes. Welcome back. We're going to continue. So I mentioned environment variables. There are some useful environment variables you may want to include in your job scripts. The temp directory, all uppercase TMPDAR. This is a local disk, 1.4 terabytes. By local, I mean it's plugged in directly to the compute node. The scratch space, that is actually, if you're going to read and write files from the compute node, that actually has to go across the network to write to the disk space. But for the temporary disk, the temp dir, that is a local NVMe drive that is 1.4 terabytes. And if you have a lot of temporary files, you don't need these files when whether your job completes successfully or whether there's checkpoints or whether it fails. You can use this temp directory, and it'll be quicker than writing across the network to the scratch space. So this is an example You don't have to know how to use SAM tools, but there's a tool called SAM tools. So if you run this, you can do a sorting, and you can specify the temporary directory. In this case, it's a prefix. You specify it using the environment variable and then the prefix you want to use. In some cases, software may say the temp directory, give me a link to the temp directory. Then all you need to do is the option and $ tmpdir. You don't have to add this other part. It's just a way to access that variable. It's created at runtime. It's different for every job. So if you're going to go into a login node, you're not going to see a value for temp dir. It actually contains the job ID and the name of the directory, and it gets created when your job starts and when your job is finished. Whether your job completed successfully or failed, that directory gets deleted. Slurm CPUs per task, we mentioned that earlier. Array task ID, we're not going to do arrays, we'll skip that. Job name, you may want to use the job name in some of your output directories or output files names. You can capture it using this variable. Node list, you might need to send your software a list of nodes that it wants to run on. That's available. Slurm job ID, that's created at runtime, or that's populated at runtime. And then if you need to capture that, you want to use it in the name of the output file or anything else, you can capture that with that using that variable. These are standard that user and Scratch and home is not here, but these are variables that are when you log in, these are populated. Your user is actually your username. Scratch is a directory to your is a path to your Scratch directory. We mentioned OMP num threads earlier. Sometimes you have to set that if your software uses that variable. You can also get your present print working directory. All right. You can see what's in that variable. Just use the echo command and the variable name. OMP num threads. Yeah, that defaults to 1. You can set that if needed, change that value. All right, so now we're gonna get a JavaScript and we're going to submit it as a job to see how we can monitor resource usage. So we have a tool called GCA templates. It's mainly has bioinformatics job template scripts. We have very few right now, but we have one we're going to use to submit a job. These templates are basically a pre-configured job script to load a module and to run a default command using that software using a small example data set. And generally, if you run this template script, it will complete in less than 15 minutes, usually within a few minutes. So run these commands. You want to make a directory called Scratch Slurm class. So you can copy and paste these 3 commands or just type them in. All right, made the directory. We're going to go to that directory. Alas, there's nothing there. It's a new directory, and we're going to run the command, which is GCA. You can type in the first few characters and hit tab. All right. Anyone get to this point? You want me to go over that again? Make a directory, go to that directory, and then run the command GCA templates. As we add more templates, you'll see more categories. And right now we have just a few. But what you can do is search. You can select the number 1 and go through the menus and look for something, a a template that has BBmap in it, or you can search. It'd probably be easier just to search BBmap. So it actually shows us which category it's in, FASTQ files, and the task is error correct and normalize. And then the tool is BBmap version 3890. So we're going to select that version or that tool. It's the only one available. In the future, you may see several tools, or you may see BBmap with more than one version. All right, in the options, paired in library, there might be a template script for paired in library. There might be a template script for single in library, and that's just the way a DNA sequence is saved into output files. But just for this example, you don't have to be familiar with DNA sequencing. We're just going to select number one, the only option available. Then it's asking, do you want to copy this script or start over, or do a new search or whatever? Yes, we want to copy it. It's a reminder that this is just a template. You need to read the documentation to see other options that aren't in the default that's set in this template. You may need to change the SBatch parameters, increase the runtime, memory, or cores to match your data. And also check for newer modules, either newer module versions, so you can check, see if there's a newer BBmap version. If there's a version 3910, for example, we only have a template script for 3890. You can most likely just change the module name to the newer module, and usually the commands are the same, but sometimes the software will change which commands, which options to use, or even how the tool is used, just based on a newer version. So you might have success just updating the name of the module. So we're going to see what's in this module, what's in this template. So we have the SBatch parameters up top here. You can see a schedule for 1 day, 1 task, 96 CPUs. So we're going to use the entire compute node to get this done as quickly as possible. Here's our module purge line, loading the software. There's some links for the manual. Tells you about what this does, and then there are these three sets of variables, the inputs. Right now we have example data set so that you can run this job without really changing anything. And sample parameters, assigning these in variables and output files, just for this example, which you can definitely change to match your data set. And then we have the commands that are actually used. Job stats, this is a tool that we have that will monitor CPU usage. If you're using software, or actually if you configure the job with a GPU, it will monitor GPU usage. So if you have software you're running on GPUs and you want to see the usage stats of how the software used the GPUs, then it'll create a graph for each GPU that you configure. In this case, this is just a CPU job, so we'll only see the CPU stats. Then there's a couple of commands here. It's going to do some error correction and then do a normalization of reads. You don't have to know what all this is. This is just a template, and we're going to use this to get an idea of how to submit a job and check resource usage. And then at the end, the last command is to run the job stats again. The first time it's in the background, that's when it does the monitoring. The last step will actually create the graph. If your job fails before it gets to the last step, you can still run the job stats command on the login node, and it will create a graph of what it used up to right when it failed. And then we have some citation information. If you do a publication, let us know and we'll add it to our acknowledgement page. So now we have a template script. We want to submit that using the SBatch command. So basically, SBatch, it's kind of a long name. So if you type in run and hit tab, since there are no other files that start with run, it will complete the name for you, and then you can submit it that way. Now, as soon as you submit it, type in the next command you want to run is sq-me. This will show you your jobs and the state of the jobs right now. The job is pending. You can hit up arrow, run that again, it's still pending. And you can run it again, and now it's running. You can see it landed on node AC006. And it's already been running for 5 seconds here. And we'll check on that often. It'll only take a few minutes to complete that job. Since we are using 96 CPUs, it might be done already. No, still going. Okay. So it basically shows you your job ID, which got created at runtime. So some of you, if you've submitted this job, just post your job ID in chat. I want to see, so we can see, probably if you submitted the job after me, you might be job number 5431. Because this is just a sequential number. So far there's been 5,430 jobs run on ACES. This can get up into the millions yep, someone right after me, they're 5431. So yeah, our other clusters, we have the job IDs up in the millions. Just because they've been online for several years or many years. All right, that job's still running. We'll let that run and continue on here. So now here is a way you can see the CPU load. If you just want to see it on the command line, you can use the PEStat command, and then you can use the environment variable user, which will populate it with your username. So just run PEStat -u user. But what it'll do is it'll show you the usage load, CPU load, every 3 minutes. Now this is useful if you reserve the entire compute node, because if you only reserve half the node, it'll show you the CPU load for the entire node. So if you only used half, there could be a job running on the other half that could be using that could be part of this CPU load. So a CPU load of 95, almost 96. CPU load of 96 means that all 96 cores you selected are running at 100% or close to 100%. This last line here showing you it's in red. CPU utilization is very low, even though you only requested 28 cores. The CPU usage is very low. It could be that at this point in time, your job is only using 1 core while it does some processing. And then if you were to check it 5 minutes later, it could be at 28, 27, for example, out of 28. So it updates every 3 minutes. So you really don't need to use the watch command and watch it every 2 seconds. Just you can update every 3 minutes to check it. But let's see. Our job is still running. That's fine. All right. So monitor running job. S-control show job ID. So this job is only for a running job, and when the job completes, about 10 minutes after the job completes. If you run this command tomorrow with your job ID, it won't work. You can put this in your job script if you want to capture this information. There's just a lot of information here about which node it was run on, AC209, how much memory and CPU you configured, or how much is on the node, how much you configured. Some other information about the directories, the working directory, where this job was submitted from this directory, start time, submit time, run time, lots of time here, lots of information. If you want it, it's there. Let's see if we can do it here. Show job and then 5430. All right. So this is my information about my job. Let's see. Oh, job state completed. So it actually did complete. So if I run the SQ dash dash me, it shows my job is not running anymore. It's completed. But if I run this command 30 minutes from now, the S control command, this information is gone. So if you want to save this information, you can put it in your job script. So let's see. All right, once your job is complete, we can see this job efficiency stats. So let's run, and the job ID 430. So it shows it was completed. Exit code, that's good to know. An exit code of 0 means it completed with no errors, nothing sent to the standard error. You might see a state that says failed, exit code 512 or some other exit code. It doesn't really tell you that much other than it's not a 0. You'll need to search the log files, software log files, standard out and standard in. So let's see what we have. We see the files. Here is our standard error file. Here is our standard out file. Notice it appended the job ID towards the end, and it also appended the job name. So we can do one useful command is ls-lsth that I use. And what it does, it puts the newest files on top. So if you have 50 files in here, if you just do ls, you're going to be searching for the file that your job script just created. You can do ls-lsth, it sorts it, the newest file on top. You can see by the timestamp here. So we have an image here. This is from the job stats utility. It created an image of CPU utilization, standard error. There is something in standard error. It's probably just information, probably not an error, probably just this tool is sending out log information into the standard error. So even though the standard error has some information in there, it's not an error. It's just what was happening at runtime. But you still want to check it and make sure there aren't any errors. These last two, you can ignore these. This is not related to your job script or their software. Standard out. It's just some information. This actually comes from the job stats command. Echoing the job ID helps to debug it later, and also it's in the name of the file, but also it just tells you some. This actually the tool itself didn't have any output. Those are actually log files from the job stats. So how can we view this? How can we view this image? We actually have to go back to the dashboard, go to files, and then go to Scratch. All right. So where's the directory we created? Scratch. Slurm class. All right, Slurm class. Here are the files that got created. So Scratch. So files. This will take you to your Scratch. And remember, we created a directory called Slurm class. Go to that directory. And the image file should be here. It's right here. So you just click that and it'll open for you. So this is really interesting because it shows you the CPU percent load. This is a scale from 0 to 100. If all cores were used 100% at 100% for the entire 4 minutes that the job is running, this red line would be maxed out up here. But you can see it was only about halfway utilization. There were probably multiple steps, so that's why you see different values for the percent load. Now the percent load is the percent load for the entire compute node. If you submit, if your job script, you configured only one core, then the percent load is going to reflect any other jobs that are on that compute node. So if you're going to use job stats and want to get an idea of resource utilization, you'll want to exclusively reserve the node for your job. And the way to do that is to request all the cores and all the memory. Now the blue line is the memory here. You can see that the first couple of minutes it only used maybe about 20 gigabytes of memory. And then there was a step here where it actually jumped up to 200 gigabytes of memory utilization. So if I was to go back here, let's go back to here, our SEFF command for the job, which is 4. It showed the maximum gigabytes was 184 out of 480, which is 38%. So it used about 185 gigabytes of memory. So if we look at this graph, it's actually at about 200. The reason for that is there's about 10 gigabytes of memory reserved for the operating system. So this is when you have the job plus system operating system. Total is the total memory from the job and whatever memory is reserved for the operating system. So that's why you see it at about 210 max. But if you were to look at the SEFF command, it's going to be a little bit less than that. So this is a if you want to get an exact amount, you can get it from the SEFF command. Otherwise, if you can just get an idea of how much memory was used. And there is this cache value here. This can be there wasn't a lot of memory in cache. That's not counted into the memory efficiency for SEFF. But it is interesting to see some of this, how the cache memory is used in different applications. So this is a useful tool. You can save this later. It tells you cluster name, job ID, how long it took to run, 4.5 minutes. This is CPU utilization. If you run a job with 2 GPUs, it will create 2 graphs, one for each GPU. If you run it for 4 GPUs, it will create a graph for each GPU. All right, so we're done with that. You can see you can look at any of the other files if you need to. Some of these files you're not going to be able to open them in the browser because it's a zip file. You don't need to open that. So be aware also how big the file is before you try to open it. You don't want to try to open a 3.6 gigabyte zip file in the browser. But some of these other files are kind of small and you can view them. Like this is stats.io. This is actually for the temp directory. Well, let's just look at the stats for CPU. That CPU. So this is actually it monitors the stats, and this file is parsed and the file is generated. Okay, so here's an example of if you were to run a job script with 2 H100s and you put job sets in there, you ran your command, and then when you look at it, when you look at the graphs, you see one graph has some GPU utilization and the other one does not. In this case, this tool, this is just an example. I actually ran a job. I looped through it 3 times just to get something to show up in the graph. And this piece of software, this is AlphaFold. So what it did is the first 90% of before the command completed was run on CPU, and the last 10% it was using the GPU at close to 100% here, a lot of the memory. And then that command was complete. I ran a second AlphaFold command, and actually you can see that the CPU part was a little quicker this time, but you see the same pattern here once it starts to run on GPU. So this is output for GPU. We already saw CPU. And then finally the third AlphaFold command completed, and you can see towards the end. But AlphaFold can only utilize 1 GPU. So in this case, if you didn't know that in advance, now you know that the second GPU was idle for the duration of your job. So next time, configure it with just 1 GPU, and also search to see if the software actually supports running on multiple GPUs. Because right now, AlphaFold does not run on multiple GPUs. All right. See all your jobs for the current fiscal year. Or this is actually going to be for your just all of your projects. You can do this. That's J all. So we don't have this working right now, but in the future, this may be useful. Basically shows you your project account, the job ID, and this will actually show you some of the stats of when SUs are enabled. It'll show you how many SUs were used for your job. One thing I didn't mention that you may know this, but if you submit a job for 7 days and it completes in 1 day, you'll preach your charge for 7 days in the future, but you'll be reimbursed for the 6 days, reimburse SUs for the 6 days that it didn't run. So you're only charged for in the end for what was running. This is a good way to see later how long your jobs ran and the total SUs that were charged. In the future, we will enable service unit charging. This is how it works. Basically, one service unit is 1 CPU per hour, or 1 chunk of 5 gigabytes of memory per hour. So this first row, if you configure a job to use 1 core, 5 gigabytes of memory, and no accelerator, such as a GPU, and you run this for 1 hour, you'll be charged 1 service unit. If you configure to use 1 core and you're into the second chunk of 5 gigabytes of memory, you'll be charged 2 service units. 1 core, all the memory, you're going to be charged for all the cores. So all the cores, all the memory, you're charged for all the cores. So if you're going, basically, if you're going to use all the memory or all the cores, just reserve the entire node, all the memories, all the cores. There will be an additional charge for the accelerator. We don't have those numbers yet, and as of now, SU charging is not enabled. All right. Dashboard. We have a dashboard where you can see your disk quotas, and you can also check your account balances. Right now, you may not have a balance showing up. Let's just go and see what we have. Dashboard. It is okay. We might have some information here. So I do have a couple of accounts. You might see on one account, 1 or 2 or more accounts based on your project, showing you actually this cluster statistics. This is you can mouse over and see what percent, if you want to get the actual number of allocated, mixed meaning partially used, and idle meaning there's no jobs running on it. Check your balance. You can also create a help desk ticket or request software installation. And for disk quotas, you have a default 10 gigabytes in your home directory. This is not, you cannot increase the space in your home directory. This is maintained as 10 gigabytes. If you want to do all your work in your scratch directory, and this is by default, it's 1 terabyte. If you have a lot of data files that are large and you need more than 1 terabyte, you can request a quota increase. And this is a temporary increase, and for your project, and it's a 6-month extension of your quota, your scratch quota, whether it be your disk limit or the number of files. You can see the number of files here is 250,000. So if you need more files, some software creates a lot of files. If they are temporary files, remember that take advantage of that temp directory, and because the files in the temp directory do not count against your quota. You can write 1 million files to the temp directory and it won't affect your quota. But if you write 1 million files to the scratch directory, it affects your quota. And you can pretty much guess that writing 1 million files is probably going to be faster to the temp directory instead of writing across the network to the scratch. So take advantage of the temp directory. For another reason is to not to help prevent you from reaching this file quota. All right. Debugging job submission. What happens if your job was not scheduled? Most of the time you'll get a message from Slurm. In this case, their message here is CPU count per node is not satisfied. So in this case, if I submitted a job and I requested 1,000 tasks per node, well, you can't run 1,000 tasks per node in one CPU per task because there's only 96 CPUs. So instead of that job getting sent and waiting in pending state, Slurm will tell you this, we don't have a compute node like this. So we need to reconfigure it and resubmit. Again, use the max config to help you out with that. If you're out of service units in the future, use my project and it will show you your balance. And remember, your balance can get down very low when you submit a job, but if your job completes early, you'll get reimbursed those service units a few minutes after your job completes. And so your balance might be 1 after you submit your job. If your job completes earlier, it might jump back up to 4,000. So maybe you can't submit 5 jobs at once, but you can submit 1 job. When that one's complete, you'll have service units reimbursed. You can submit the next job. But for now, you don't have to worry about that because we aren't charging service units yet. But in the future, you can refer back to this slide for reference. If your job is pending and you're not sure why, you can check how busy the cluster is that we mentioned earlier, sinfo command, or you can go to our main website and check that percent core usage statistic on the left panel. You can, if you're running a GPU job and it's not launching, you can run the GPU avail command, and if there are no GPUs available, it'll show that there are none available, and that's probably most likely why your job is not launching, because there aren't any GPUs available. You'll just have to wait. I remember there's a 2-day max limit on the GPU partition, so hopefully you don't have to wait longer than 2 days to use the GPUs. We also have maintenance scheduled every now and then. Not that often, maybe every month or 2 or 3, but definitely not on a weekly basis. But if you schedule a job to run for 7 days, for example, you can run the maintenance command. Let's run it right now. Okay. All right, there's no ACES maintenance scheduled. If there was, you would see something like this. The scheduled maintenance, usually it's 8 hours or a little bit longer. It'll tell you when it starts. So if you submitted a job for 7 days and it's not running, you can run the maintenance command. And if it says there's a maintenance starting in 3 days, your 7-day job will not start because it overlaps with the maintenance window. What you can do is, if you think your job will complete in 3 days and 16 hours, then you can reconfigure your 7-day job to run for 3 days and 16 hours. Then it will launch if you can do that within 41-minute time of running this command, the maintenance command. So this is useful if your job's not running. Do these 3 things before you send the help request, because these are easy to see if the nodes are busy, GPUs, or if there's any GPUs available, or if there's a maintenance coming up. To help diagnose why your job's stuck in the pending state. Completed jobs. Look in the standard error output. We looked at this BBMap standard error output, but it was mainly information from the BBMap software. If you see something like this, it seems a little cryptic. Slurm step D error exceeded job memory limit at some point. Most likely that is due to your job running out of memory. You can check the SEFF command. Remember, no, it's right here. if you see this command in your standard error and then you run this command, you might see 99.9% of 480 gigabytes. Memory used all 488, or I only use 480 here. So you might see 100% used. In that case, you need to use a compute node with more memory, or you need to reconfigure your job to use the less memory. Also look for some of these keywords: out of disk space or no space left on device. If you see those in the standard error file, check your quota, show quota, to make sure you haven't reached your quota. For example, if I have 1 terabyte is my limit of disk space, and I see 1.1 terabytes here or 1.0 terabytes, that means my usage has met my limit. So I'm unable to write any more files, and the software cannot write any more files, and the job fails. Same here, if you reach 250,000 files when your job's running, you're going to reach this limit, and the job is going to fail because you've reached your quota. So check the output, search for these, search for memory in the standard error file, search for space, disk space, search for the word error, and just read throughout the standard error file. Usually the key to resolving a failed job is in the standard error file. All right, reduce number of files if you reach your quota. Delete non-essential temporary files. Remember the temp dir, that's useful, very useful. When you're done with the project, you can create a tar.gz package and then download it from ACES to your local computer and save it somewhere. And then you can delete the files from ACES so that you can free up disk space. And if you have a project you're working on and it's going to require a larger amount of disk space, then you have in your quota, you can request a temporary increase. You can do that through the dashboard that we showed earlier. All right. There are other apps available on our dashboard, on our portal. If you have an application that launches a GUI, a graphical user interface, you can use the VNC app, and it will basically load a terminal on a compute node. It's basically scheduling a job to run on a compute node, and then you can log into that compute node using a web browser. So if I launch a VNC job, if I launch it using 96 cores, and let's just see what we can do. So whatever job I launch here is basically like launching a job from the command line, except it's going to you can access it through the browser. Okay, so we have a few apps available. These are very useful apps. Basically loads the environment for you and presents the GUI and the web page, so you don't have to. So you can work through a web browser. When you access the command line, again, limit your processes to 8 cores. If you need more, you can create a job script. And you can also monitor raw jobs from here. Go to the jobs, active jobs, and it will show you any jobs that are running. Right now, I don't have any jobs running. All right. All right. We got some information here. If you want to contact us, if you have any questions or comments about this short course or about anything we have on our system, or from whatever you might find in our knowledge base, check out our knowledge base. It has a lot of information specific to ACES, but we also have information about specific software, how to run it on our systems, what you might need to add to a job script in order to get software running on our systems. Check the user guides. And if you have any questions, here's our, you can send a message, or email to help@hprc.tamu.edu. All right, does anyone have any questions